Hello, everybody. My name is Norbert Kozsir. Thanks for coming to my talk, Building a Video Editor and a High-Performance Rendering Pipeline with Flutter. So I like to build stuff, and building stuff is fun, but what is even more fun is launching stuff, telling the world you built something, you did something. And I really like to create videos, short teasers, things to post on Twitter, maybe LinkedIn, other landing pages. I was always struggling creating these engaging, fun, nice videos because software tended to be very complex, overwhelming, and like not holding my hands to what to do. I'm not very artistic. So that's why I decided to work on this project called Cutscenes, which is a video editor, as you might have guessed from this talk, written in Flutter. I quickly want to show you a demo because this is like the project this talk is based on. So this is a macOS app. This is fully written in Flutter, and I prepared a little demo. And basically the idea is that you can have a screen recorder inside, you have animations, you have effects to do great videos which are cut together and launched. So I just recorded my screen for this presentation, and you can see there's a video playing in Flutter. We can go in there. We have like these zoom effects where we can change the amount, the zoom level. We can do XYZ transformations. We have different animations playing. And at the end, we can just hit export, and we get out an MP4, which, depending on the length, might take a second. Okay, something is, demo effect, maybe because the screen thing. But anyways, so let's continue with this. Before diving into the fun stuff, I want to first quickly talk about how video actually works, because that will be like the fundamentals of everything I will speak about. In the very essence, video is just a bunch of frames shoved together. We have frames playing after each other, creating the illusion of movement in a video. You may have already seen this, and as a kid may have already created some of this. A very simple example is like a flip book, where you draw a bunch of frames, and each frame is flipped through, and you get the illusion that there is a video playing, even though it's just single frames. So I talked about frames. This should be or could be pretty clear, but what is a frame? So a frame can be represented in a bunch of ways, but the typical representation is RGB. So it means every pixel is represented by an intensity of light for the red, green, and blue channel, and a combination of those result in colors ranging from completely black to completely white when all the colors are active. A lot of modern monitors actually work this way, where every pixel has like 3 different colors, and they vary in intensity, resulting in color. And using this, if we take 8 bits per channel, so for every color, there's 8 bits of information stored. That's 265 different possibilities. We get about 70 million colors. So that's a bunch. We can represent a good amount of color with that. So if we just take the simple approach of having video being frames put together, we have a problem. So let's do a simple calculation. Let's say we have 24 bits per pixel. That's already, we have a HD video that's already 2 million pixels per 920 times 1080. It's already about 6 million bytes per frame, so 6 megabytes per frame. 30 frames per second, it's already about 200 megabytes a second. Let's say we have a typical YouTube video, which is 10 minutes. So that's 112 gigabytes of data that you would be downloading for every single YouTube video you would be watching, which is not feasible. And this is where codecs come into play. Codecs are basically just an encoder and a decoder, and they make it so you can have videos that are actually not this huge. Just a couple of examples to give you. There's this one called VP9, which is by Google, which is very commonly used on YouTube. They re-encode stuff you upload. VP9, not everything, but there's also AV1, H.264. If you have an MP4 laying around, chances are very, very high that it's encoded with H.264, maybe H.265, which is a successor. ProRes, Apple also did their own codec. But modern video is so much more than just video. Sounds weird, but if you watch a video, you also have audio, you have subtitles, you have metadata, you have all of this, and this is what a container is. Container is basically, well, it's a container. It contains video data, it contains audio data, it contains all the metadata, and also a couple of examples. So these are QuickTime container by Apple, WebM by Google, which uses the VP9 codec internally commonly, AV1 by Microsoft, MP4, probably know these. So this all seems pretty complicated. All you want to do is have frames, video, and just want them to be as small as possible, as good as possible, and you don't want to deal with all the different calculations on how to do chroma subsampling and what's so on. So this is where FFmpeg comes into play. Quick question to round, who knows what FFmpeg is? Okay, that's a lot of people, that's good. So FFmpeg is basically a collection of libraries and binaries that allow you to interact with video and make it easier to do a lot of things. Actually pretty easy if you look at the commander interface. For example, there's the FFmpeg commander interface. This command, for example, transcodes a video, meaning you input a video, it decodes it, and then encodes it with a different encoder. And also it can be used for doing things like cutting, where you just trim something at the beginning, at the end. And yeah. So let's talk about Flutter, because most of this talk has been about video first. So when I was starting Flutter, which was in beta, you would commonly hear things like Flutter is a mobile framework. The pitch was you write code once, it runs on 2 devices, and that's great. You have this reactive framework, and that's just nice. But over time, Google introduced different targets. We got desktop, we got web, embedded is becoming a big thing, and Flutter is just so much more than a mobile framework by now. It's a UI framework. Flutter deals with pretty much anything that is UI, and UI is also, for example, video. So I subdivided the main body of the talk into 2 parts. We have the front end, which you usually call your front end, which is an app, something the user interacts with, something that you see real-time feedback, you click around, you change state. There's the backend, which I call backend in this case. It doesn't actually run on a backend server or whatever. It runs on the front end, but it is what creates the video, which is non-interactive, which just takes frames and puts them into a video. And the output is different for each. We have the output is a screen for the one, and we have an output that is MP4 for the other. So let's start with the front end. You may have seen this formula before. UI equals the state given to a function, which is typically widgets. And I still use this paradigm. I use state management for things to let people interact with the app. But for the video part especially, I have like this notion of being a bit more restrictive and saying a single frame that is like in the video area is a function given a frame number, and that's it. So every single frame in the video can be represented by just giving it the frame number, and it knows what it needs to display. So as a couple of examples, you have seen before there was these zoom and camera effects. All this is basically getting the frame number, then finding the 2 keyframes that's in between, and then doing some transformations and interpolating between 2 camera configurations, and then using these to pass them to some nice matrices and putting them into just a transform widget to transform everything that is in the video area. You also have seen that there was a video playing. So how do we deal with video playing in Flutter? So the simplest answer would be, yeah, we use a video player. I didn't do that at the beginning because we have the formula. We want a frame to be based on a frame number. And with video player, that's a bit more complicated. So I started with using this fun function, which is called precache image, which you can call to basically precache an image and load it into memory and do things quickly. So the idea was, and it worked, I can tell you in a minute why it didn't work well, but it worked, is to just call precache image for a bunch of images, more especially for every image in the video, and then just swap out images very, very quickly. It works, but you may imagine that having like a lot of frames, going through getting video into frames and putting those frames back into the GPU. And it's not very efficient in terms of, mostly in terms of memory, because you offer all the images in memory, and pre-cache image takes a bit of time. So that's not optimal. I'm sure you could do some magic and make this really nice, but I decided to switch it out to using an actual video player. You may have seen a keynote on the first day. Platform for use for desktops, for desktop is coming. It's not fully there yet, and this issue is still open. Video player adds support for macOS. Yeah, I was like, okay, we just use a video player. Flutter video player, well, the issue is still open. But I was able to find a third-party package which uses textures to have a video player. The issue with the video player was really weird. You think time is absolute, like, you know, time moves forward, it moves forward the same amount of speed, but that's not the case here, because it turned out I was using a ticker, a simple ticker to increment the frames every time something happened, and then just click the delta and update it to the next frame. But when I was using a video player, stuff started to diverge. The animations were suddenly out of sync, starting the video and stopping it again a bunch of times turned out to be a full mess. This is because like it all went through the platform channel. Stuff was always a bit delayed and a bit in a different speed. So a quick hack, which isn't perfect, but I wanted to mention it, is just using the video as a source of truth when it came to time. So every time it updated its state, we're just saying, yep, we use that. The internal ticker is wrong, the video player is right, and just having this authority. When the video is playing, it knows about the time. There's no video playing, the ticker knows about the time. So all of this results in, we can just play a video. We can hit play. You see the video is playing, the animation, it's fully synced with the video. So every single frame is at the correct time. There's no divergence, there's no weird things happening. So that was the, I'd say, easy part. We know Flutter, we write front-end apps, we know how to use a video player. But now comes the tricky part. How do we actually use Flutter to create a video render where the target is not a screen, but actually a video? So I want to take you on a quick journey on this and basically show you what I went through and kind of take you on a journey of starting with something that works. Doesn't work well, but it works, and optimizing it gradually over time. So let's start the slow way, but the simple way. So how do we get frames out of Flutter and put them into a video? Simple, we can just use a repaint boundary. So basically what a repaint boundary is, it's a widget that creates its own layer, and it makes it so the painting is on a different layer, the GPU can do a bunch of fancy things. And there's this fun function where you can find the render repaint boundary, so the render object for the repaint boundary, and we can actually call toImage on the boundary. And if we call toImage on the boundary, that basically goes to the Flutter engine. It then rasterizes the whole thing. It's all async. It sends the result back as PNG data, as PNG bytes. In this case, I'm printing it. Obviously, you wouldn't be printing it, but saving it to a file. And doing this because the backend there is no interaction in the backend. In the front-end, users start playing, they stop playing, but in the backend, it's just a rendering process that does its thing. So it's just a Flutter app, basically, that is running in an endless loop while true. Probably not the best case, not the best idea to use a while true, but a for loop instead. Just wait for a frame to finish, increment the frame, and call setState. And in between, you would do the give me the PNG data for that frame. And the result of this, before that, and basically for showing the video, we could still use the frames. So we could have the video split up into single frames, shove each frame into a folder and just index every single frame by its frame number, just put it into an image. Because in the backend, we don't care about being real time, we don't care about being like the most performant, we can just, at the end, we want something that is correct. And the result of this is like this. We have a folder full of images. They're all PNGs. And this is great. We can use ffmpeg, for example, and just use this command, give it the folder, and it takes all the frames, puts them together, and we get a video out. We can choose our encoder, we can do all sorts of fun things. And the architecture of this is pretty simple. You have your Flutter app. It's just the Flutter app that is actually running. You can see what it is doing, and it saves the frames. You get this big folder full of frames. You put it into the FFmpeg CLI, and you get a video out. It's very simple. And it has some pros. So this approach is actually pretty cool because it works. Yeah, that's it. But as you might imagine, it's very slow. So you're going through like GPU to rendering stuff, then going back, then going to the disk, then going back to like FFmpeg. It does weird things, CPU, memory, and it also, the folder becomes really big. Like if you have a video that is like, I don't know, 2 minutes, we're not dealing with raw PNG data, RGB data because it's PNG, so the files are a bit smaller, but yeah, 10-minute YouTube video might be, yeah, it could be 100 gigabytes, this folder, and you don't want that. A Flutter window is running, you want it to render, you don't want this thing to kind of run and you don't want to see it and maybe mess things up by accidentally closing it or whatever. And yeah, it has a very high disk usage, which I just said. Okay, let's tackle one of these problems where we want to go headless, meaning we want to not have a Flutter window running anymore. We want to have it so that it is just this background process that it's processing. Of course, we're using widget tests for that. What else to use? So widget tests, those are things which is very unique to Flutter, I'd say, because you can actually test the UI in a sort of mixture between, it's a unit test and like an end-to-end test kind of. It's not an end-to-end test, of course, but it's actually dealing with UI. So how can we use widget tests to do rendering? Golden tests. So who knows what golden tests are? Okay, a lot of people. So golden tests are basically a way to create tests that actually test UI by comparing pixels. So the idea is that you write a test where you know it looks good right now. The golden test takes a screenshot of that, saves it, and the next time you run your golden test, it checks pixel by pixel if the images are the same, which is very useful, very custom UI one to make sure that everything stayed the same after you change something. We can abuse that. We can use that mechanism and do this. We can basically create our own test. Even better, we can create a bunch of tests. More specifically, one test per frame. We can then load our widget, our video widget for that specific frame. We can then do this pre-cache image before doing our golden, and then we can just say, yeah, matches go. And we don't care about matching, like we don't use that feature. All we do is basically, yeah, take the screenshot, please. And the architecture is very similar, but instead of just having a Flutter app, we have a golden test thing running on top of that. Nice thing is, we can even parallelize this. Like, I didn't do exact measurements on how big the efficiency gain was, but I had a small script that basically took the number of cores I had and just subdivided the number of frames I had and said, okay, core 1, you do the first 20 frames, core 2, you do the next 20 frames. This was better. Actually, this was the first approach I took. I never really did the one before, but I wanted to mention it as it is even simpler. Yeah, small meme. It's really not that fast, but it solved one of the problems of being headless, and it felt like a rendering engine. It was like, okay, we click a button and it does its thing, and when the process finishes, we have like this video. So next step, how do we make this even faster? Before we talk about this, we need to talk about embedders, what they are, what they're used for, and how I used embedders to do things better. So you may have seen this graphic once or twice already on this conference, but this is the, from the official documentation, this is like the architecture of Flutter itself. At the very top, we have the framework, and the framework is basically what you interact with most of your days. You have your widgets, you have your render objects, you have all of the fun stuff. And this is also where obviously most of it is implemented, but we don't care about this for now. Below that we have the engine. This is this mythical place that does a bunch of very hard stuff. And we don't want to touch it either. What we care about is the embedded, very at the very bottom. The embedder basically is the glue between the engine and the system it is running on. So it does things like hooking up the engine to display frames to the display. The engine needs a callback to show frames to, and the embedder provides that callback. It also does things like native plugins, the platform interface. It does threading setup, event loop setup, and it's all very system specific. And there's a bunch of embedders. For example, an Android, there's an Android embedder to run on Android. There's a Windows embedder, macOS embedder. And all of these embedders do is basically make it so Flutter and the engine runs at that platform. The engine is actually pretty simple, so to say. It's not, but it's a single header file. If you know a bit of C++ and C, a header file basically is just a file where it defines what it can do, what stuff you can call, and all things the engine can do are inside this header file. So if you have the header file, you have a built engine, you can just have a C++ project that does things with the engine. And one of those things you can do with the engine is actually override this function called software service present callback. This is a very simple function. It takes in user data, which we don't care about, and a void allocation. This is basically an array of RGB data. So if you override this callback, this will be called every time a new frame wants to be presented. More specifically, if you call setState or whatever other mechanisms trigger a new frame in Flutter, this callback will be called, and you should be responsible to show this frame to the user, but we can do different things with it too. We can create a custom embedder to use it for video rendering. So as I said, the embedder, there's a bunch for iOS, Android, but what if we create a video embedder, which target is not to show frames to the user, to let users interact. We don't care about resizing, we don't care about events. All we care is about taking frames Flutter produces and putting it into a video. So building a custom embedder is also, relatively speaking, not too difficult. I didn't have a lot of clue about like C, C++ and everything. But essentially you just have to call a few setup things. There's a bit of documentation. It's mostly that you don't have to do too much. Even more fun, it's C++. So using Dart, FFI, you could even create an embedder in Dart and just call the C functions from Dart side. So you could have the embedder itself be Dart. This is just a small code snippet of showing like stuff you have to do. You have to set up a Flutter engine display, do some call embedder.run with some arguments and so on. And at the end, if you build your project, you get out an embedder, which is just an executable, and you point it to the folder where the build is. You can obtain it by either running Flutter run, and there will be a build artifact, or just use Flutter build, which just results in a folder. And given that, the engine will then run this thing. Same as in the approaches before, it's just a loop which, without any user interaction, just chugs through all the frames. In this case, we have our Flutter app. We have a custom embedder that doesn't display anything. It's just fully running in the background. And on every frame callback, we then still save all the files into a folder, use the CLI FFmpeg, the FFmpeg CLI to create the video. So this is way faster, as you could imagine, using golden tests. But we still have the issue of having images. So can we go even faster? And the answer is yes, we can. That's the issue. We have a bunch of frames. We don't want to involve the disk in this. And at the beginning, I said FFmpeg is a collection of libraries and programs. Up until now, we only use the CLI, but we can actually also use the library it provides. In this case, I use it as a dynamic library, which just exposes functionality to native code. And there's a bunch of boilerplate code around this. Doing this there's a lot of digging through old documentation of FFmpeg is, not in a way that is old, that it is bad, but it is like FFmpeg is a big project. And using the libraries, we can use things, for example, like AVCode extend frame, where we just pass the YUV frame, and it does its own thing in its thread, and we don't have to save anything to disk, and it's fast, and it's nice. So this greatly simplifies our architecture. We have the Flutter app, we have Flutter, which runs the Flutter app, which runs on a custom embedder. And on the frame callback, we shove it directly into the video without going through the step of PNG data into a folder, into the Bex UI. So can we go even faster? Yes, we can. The graphics card. Up until now, this was software rendering, very CPU heavy, but the graphics card is actually very good. Who would have known at doing graphics? So involving the graphics card is as simple as, for example, using OpenGL to do the rendering instead of doing it in software. OpenGL is basically just a specification of how to talk to a graphics card. And the Flutter engine provides ways to use OpenGL as its rendering target. More specifically, very simplified, all you have to do is, instead of using the software surface rendering callback, you use the OpenGL present callback. Of course, there's a bunch of other setup and so on, which I didn't want to include because this is no OpenGL talk and there's a bunch of setup to do. But essentially, we do some OpenGL magic in there. More specifically, I used pixel buffer objects, if anybody is deep into OpenGL, and use direct memory transfer to always have 2 frames that is rendering to, because the big bottleneck was you render a frame, which is fast, but then you have to pull that frame from the graphic card into the CPU to give it to FFmpeg, which is slow. So what actually is happening, it is drawing to this pixel buffer object, which is basically this off-screen canvas, and then it uses direct memory transfer, which is a feature by the operating system where it can map memory to a location. And while it is doing that, it just renders the next frame to the other canvas, which is now stale. And once that's done, it just swaps those 2 frames, and there's always stuff happening, and there's no like waiting for transferring memory to then drawing something to transferring. And this greatly improved the performance, especially when rendering video, because video is like, it's this big file, it has a higher resolution, and it's a bit harder. A couple of slides ago, you saw FFmpeg expects a YUV frame instead of RGB. So what is YUV? There's a bunch of history to YUV, which I really don't want to get into, but essentially it's just a different representation of a frame. The end result is pretty much the same, but the channels describe something completely different. In RGB, every single channel represents a light that you combine. And in YUV, the first channel represents the brightness of that pixel, and the U and V represents some sort of color shift that you can apply to receive the correct color. This is great because it turns out the human eye is way more perceptive to lightness and darkness than it is to color. So we can actually use that to compress the color data more than the lightness without looking like a different image. And this is useful also in video, so that's why YUV is commonly used. FFmpeg, as everything else, provides functions to convert RGB data into YUV. And that worked, but turned out this function was slow. Why was it slow? It's running in CPU land. And on the CPU, this was really a bottleneck. I noticed, okay, what is taking up all the time? And this single function call was just really slow. So I experimented around with using compute shaders and shaders in general to do like this conversion in the graphics card, which is just a bunch of formulas. But yeah, I stopped because it was, I don't know, hard. So I decided to use just a thread pool where we get the frames, put it into a threaded queue, and then every thread just picks up the latest frame and spits them out in the same order. And this resolved the bottleneck of having to wait for all the color conversion. So because that's pretty sad, you have a nice fast rendering engine, you have a nice fast encoder thread, but the whole bottleneck is just converting the same color to the same color, just using a different format. Like the first time I measured to the last time, approximately on my MacBook here, I had about a 16x speed up, which is nice. So at the beginning, using golden tests, about 1 minute of video took about 16 to 20 minutes of rendering. Now it's pretty much real time. Yeah. So we talked about rendering. Now I want to talk a bit about macOS. Cutscenes is macOS only right now. Flutter is cross-platform, but there's a bunch of native libraries which need some sort of compilation target, And I decided to just support macOS first and worry about all the stuff later on. And at the very beginning, when I was building this, you were greeted by this nice screen if you didn't have FFmpeg installed through Brew, which basically told you, please install it through Brew. And this isn't too great. This has a couple of problems. First off, if you download an app, you don't want it to be forced to run this weird command. If you don't know Brew, it looks scary. But more importantly, this takes a long time. So ignore the glfw for now, but just ffmpeg install brew install ffmpeg. Brew likes to compile stuff from source, and this command I saw it take like 30 to 60 minutes on some machines. Yeah, you don't want to do that. At the end, the binaries and everything is small, but it just takes a long time. So I wanted a way to kind of ship ffmpeg and kind of have it all bundled so it just works out of the box. So if you have a Mac and you have applications installed in your applications folder, you can actually take a look what is inside. Similar to Java, an application is just basically a folder with a bunch of stuff inside. So we can take a look and see what's in there. And as you can see, I put a bunch of ffmpeg binaries and so on in there. Yeah. What is involved in shipping ffmpeg? First off, you can actually build ffmpeg yourself. I was really scared of this, but it turned out pretty easy. It just takes a long time because it's compiling a bunch of stuff. But this allowed me to remove a bunch of stuff I wasn't using, remove flags, just do things I really wanted and needed, and also something else, which will be the next part. I needed to update the R paths. Looks innocent enough, but this one was a real pain. And bundle everything up in an executable, put it in the right places, configure the paths correctly, make sure everything can be found, and at the end sign, and so on. Yeah, R paths. So the thing with R paths is these dynamic libraries have something called R paths or executables on macOS, and these are basically, they point to the things they depend on. So you have this dynamic library, and it says, okay, I depend on these other dynamic libraries. And if you see, there's my name is in there. That works on my machine. That was like the excuse. Why doesn't the executable work for you? Yeah, if you have it installed on your machine, you probably are not named as I am and have this exact folder structure. So it needed to look like this, where it points, where it is a relative path inside the executable path. This was really hard. Honestly, it could have, maybe I did it completely wrong, and this could have been like one single command. But there were a bunch of dynamic libraries before I did my own custom ffmpeg installation. There were a lot, then it shrunk a bit. Yeah, I had a big army of scripts like these, which traversed it, used O-tool to essentially just change the file it was pointing to. Well, actually, ChatGPT helped me a lot. Great for bash stuff. I'm bad at bash. And in the end, it worked, condensed in like 2 minutes, but this took me way too long. One more thing with macOS is the x86 versus ARM thing that happened the last couple of years. Apple released a new M1 and M2 chips, which have a completely different architecture. The nice thing is they're pretty much backwards compatible because you can just run x86, like the Intel version of the code on ARM, and it just transpiles it to use the different instruction set, which works, and it worked, but turned out to be slow. In a lot of cases, it doesn't make a difference, but in my case, because the embedder and everything was running on x86, it was pretty slow on ARM. Yeah, you can use commands like these to just force it to transpile on to x86, so it works, but it isn't too fast. How do we make it work with ARM? I needed to build an ARM version of the Flutter engine. There's a build bot that publishes versions for a lot of different architectures and everything, where you can just click download and it works. Not in this case. Maybe by now it's there, but back then I had to build the engine myself and just change some flags. Yeah, I still have the engine on my Mac. It takes about 40 to 50 gigabytes of my space, and I'm afraid to delete it because it has some small changes that I may have forgotten. I needed an ARM ffmpeg build, so the dynamic libraries needed to be ARM because they were actually doing a lot of the heavy work, so they needed to be performed too. And again, doing all the RPath bundling signing, and that's also part of why the scripts become complicated. I needed the ARM, RPaths, they needed to point somewhere else, and everything so on. And at the end, there's 2 folders where all the binaries are in, ARM and x86. I decided to distribute them both in the same executable, so users wouldn't have to choose between which one to choose. But it increased the size, but it's like a couple of megabytes, which shouldn't be too big of a deal. And yeah, in Flutter, just use river provider where I run uname-m to check if it's an ARM target or an x86, and then just call the write backend, which is just an executable to call. Shipping the macOS app, there's pretty much two choices to do. You can use the App Store, or you can custom damage, which is like this installer thing. I decided to go with the damage, where you just click it, the installer, and you're prompted to move it to the applications folder. Again, it's just like this folder, kind of, which is the single file. And you can customize the look and feel with, I used this open source project for it. Yeah, that's it about my talk. Now, I need your feedback. Like, if you are struggling with video, if you create something, if you have anything that you're facing the same problems. I have a lot of tech, I have a lot of ideas, but I don't want to waste my time building stuff that nobody needs. So if you're interested, you can check out the website. I put up the download for macOS like a couple of hours ago. You can use it for free, test it out. Be warned, it may contain bugs, it may crash, it may also not. And I love to hear feedback. If you don't have a Mac and still are excited about this, just talk to me. I'm happy to hear what kind of problems you face. Also, I have a Discord which I set up where you can join and kind of give feedback and talk to me directly. Other than that, you can find me here, you can message me on Twitter. And yeah, thanks for listening. Yeah.